So, in this lecture, we will be talking about material particles and matter waves. And in the material particles and matter waves, we will be starting from the de Broglie relation. And after de Broglie relation, once we understand what de Broglie relation is and what material waves are, then after that, we will be discussing our wave function. So, for further details, let's talk about, let's look at this PowerPoint presentation. And the theme of this PowerPoint presentation, like in the book, it's basically material particles and matter waves. But, like my theme, which I changed it a little bit, and I made it from the discovery of photons to the concept of a wave function. So basically, we will be going and we will be discussing the wave function. So let's talk about 1900. In 1900, what happened? Max Planck, he was the first person who came and who provided a solution to the black body radiation. And his solution was an unorthodox. Before Max Planck, nobody, like all the scientists, they were thinking like classically, but he was the first person who, like introduced a new way of thinking. And he said that energy is emitted, absorbed in discrete packets, and these packets he called them quanta. So he is equal to h nu, where h is Planck constant and nu is its frequency. So it's more like classically when you talk about like when the water is flowing, so the water is flowing in a stream, and all the stream is kind of continuous. But instead of that, let's think about a bottle. So we have a bottle of water coming, and then another bottle of water is coming, and a third bottle. Now this is not continuous, but this is discrete. Similarly, if you are going, if a person is like moving up the hill, so usually there is a kind of a slope. So you are walking on a ramp. So if you are walking on a ramp, the ramp is continuous. But on the side of that ramp, like you can also see sometimes stairs. So the stairs is this concept where you have one stair and then you have another stair and you have a third stair. So this is a kind of discrete. These are not continuous. So in nature, for the first time, Max Planck was the one. He perceived the world, that in the world there are things they are continuous, but there are things they are not continuous, but they are discrete in nature. And using this concept of discreteness, he was able to explain black body radiation. Now, like using the same concept was used by Einstein in 1905, and he explained photoelectric effect, for which he received his Nobel Prize, probably in 1991 or 1992. And the same concept was used by Niels Bohr, and he was the one who basically provided a first successful atomic model in 1913. So Bohr atomic model proposed that electrons in hydrogen atom occupy quantized orbits at discrete energy levels. So he said that if the energy is like when we substitute n is equal to 1, so that energy minus 13.6 eV square. So that orbit is possible for which En is equal to minus 13.6 divided by 1 square. Then the next energy level, he says that E2. So for E2, when we substitute N is equal to 2 here, and for N is equal to 3, we substitute N is equal to 3. One thing I want to explain here, that the negative sign in this equation shows boundness. that the electron is bound to the nucleus because of the Coulombic attractive force. So this much energy will be required to remove an electron from the orbit. So from this one, it is clear that the electrons in orbits, the only possible orbits are for which energy is kind of, when n is equal to 1 or 2 or 3. So he says it's more like stairs. You can have first stair, then you can have second stair, then you can have third stair, but you can't put your, there is no place within, like the two stairs. So the same is with the orbits of the hydrogen atom. Then after his this theory, which was in 1913, then experimental verification of quantized atomic energy levels, that Frank and Hertz experimentally confirmed quantized atomic energy levels. So they were the first people who experimentally verified the quantized energy levels. Then, but the origin of quantization was not known, even with all these evidences. So there were experiments, the people they proved, Einstein, like photoelectric effect explanation, Bohr's explanation, Frank Hart, like similarly these Frank and Hertz experiments. There were so many other experiments, but like nobody knew what is the origin of the quantization. So now we going to the next level, and we are going to the next stage where we will be going from the photon to material particles. So matter waves in 20 this is 19 20. So let me correct it. This should be 1923. So in 1923, Louis de Broglie was the first who proposed that all material particles have wave nature. So this was a kind of, like you are thinking, you are thinking that all the material, if you are throwing a tennis ball that is associated with a wave, you are throwing an electron that is associated with a wave. You are basically, you are throwing, you are shooting a bullet that is also associated with what? With a wave. And the wavelength of that wave is lambda, which is h. H is a Planck's constant, and p is the momentum. Momentum means mass times velocity. H is very small. H is very, very, very small. M, like V, it all depends upon your denominator. So if you make your denominator very small, and small denominator is only possible when the particle size, when the particle mass is very small. So when the particle mass is very small, then its momentum will be very small, and ultimately lambda will be appreciable, and you can, like measure it and you can see it. But if p is not very small, it's in macroscopic level. Let we talking about a tennis ball, or we are talking about a bullet, then in that case lambda will be almost negligible. So like when we talk about matter waves, so all the particles are associated with waves, all the material particles. But in case of large particles or macro particles, what happens? The P is large and H is very small, very, very small. So if this one is large, this is very small, then lambda will be negligible. Lambda will be almost equal to 0. But if this one is small and this one is also small, then lambda will be not negligible, and we will be able to measure lambda. So that's why when we talk about electron, so for electron, like lambda is measurable. For neutron, And for hydrogen atom, for all of them, you can measure lambda, and lambda is appreciable. Now, wave nature of electrons conformation, let's talk about, like when it was experimentally confirmed. Because like this theory was totally theoretical. Louis de Broglie, his theory was totally theoretical. He predicted that all material particles are associated with waves. But what happened? The experimental verification came by Davison and Germer. They experimentally confirmed through what? Through diffraction of electron through nickel crystal. So when the electrons, they pass through the nickel crystal, they diffracted, the diffraction pattern proved, because diffraction is wave phenomena. So when they obtained diffraction, from that diffraction, they confirmed that electrons are, are associated with waves, or wave nature of electrons. So far, we were talking about, particle nature of light and wave nature of light. But now we are talking about wave nature of electrons, wave nature of protons, wave nature of neutrons, wave nature of atoms. So there was another person too, basically the Nobel Prize that was shared by Davison and German and G.P. Thomson. G.P. Thomson also basically in his experimental studies, he also showed that electron behaves like waves. And G.P. Thomson was the son of J.J. Thomson. So father, he received Nobel Prize for the discovery of electron, and son, he received Nobel Prize for proving that the electron behaves like a wave. They have a wave nature. Now let's going a little further and let's move towards the most interesting thing of quantum mechanics, that is wave function and Schrodinger equation. So let's talk about a wave function. Classical trajectory is substituted by time-varying state called quantum state of a particle, psi RT, which contains all the information about the particle. So far we were talking about a classical trajectory. The classical trajectory means when you throw a particle, so when you throw a particle, you know the path of the particle. So that path of the particle is called its trajectory. And it is a deterministic kind of, experiment that we know the future of the particle at all time. But what happened? No more for electron, for photon, for neutron, for atom. We will be not using classical trajectory, but for all of them, a new term was introduced that was a psi RT. And this psi RT contains all the information about the particle. So if you want to know about the position of the particle, so you can, extract it, evaluate it from here. If you want to know about the momentum of the particle, it is also in the wave function. If you want to know about the energy of the particle, it is also within this wave function. And you can basically, extract it for you using the quantum mechanical tools. So now coming to the point that the classical trajectory is basically replaced by what? The classical trajectories are replaced by a time varying state, which is called a wave function, And this wave function basically contains all the information about the system. Now, the second thing is psi RT is probability amplitude. Psi RT is probability of the probability amplitude of the particle's presence. So larger the probability amplitude means larger probability. Less probability amplitude means lesser probability. Then the second thing is the probability dP. This is probability amplitude and dP is probability. Usually what I have seen, the people, they cannot differentiate between probability and probability amplitude. So the probability dP of the particle being at a time t in volume element d cube r. So if the particle is in this much infinitely small, the probability of a particle in this infinitely small volume is dP. And what it says, situated at the point r must be proportional to d cube r. So this probability is proportional to this volume. If the volume increases, the probability increases. If the volume decreases, the probability decreases. If we consider all the volume, then the probability will be maximum. The probability will be maximum. So this is something, to remember that psi RT is probability amplitude and P is basically probability. Now, going a bit further, psi RT mod square is the corresponding probability density. This term, sometime most of the student, they confuse probability amplitude, probability, and probability density. Probability amplitude, probability, and probability density. And the relationship between all of them is represented by this equation, where dP is equal to C. C is a constant, is a normalization constant. And coming back to the point, this is probability, this is normalization constant, this is probability density. This is probability density. And this is naturally the infinitely small volume in which we are, looking to the probability. Now, the next point, that is the principle of spectral decomposition applies to the measurement of an arbitrary physical quantity. So, the principle of spectral decomposition, we already know that what happens there, there are quantized, results. There are quantized results. If you people remember, we discussed in polarization that there were two possible results, whether the photon was in the EX state or the photon was in the EY state. So the photon existence in EX state or the photon existence in EY state, this phenomena we call what? We call this as principle of spectral decomposition. So that was only for two-level system. But if we, if the system increases, if there are more and more states, then there are more and more possibilities. But again, only and only those results will be possible for which, your state, for which for which there is possibility of the state. Like all states are not possible. Only some states are possible. Like for example, if we say that we have an atom. So within atom, we know that the electrons are either in K shell, or L shell, or M shell. So the spectral decomposition means that either the electron will be in what state? In K, or L, or M, or N. This will give us basically what? The spectral decomposition. Now going a bit further, and we will be discussing Schrodinger wave equation. So like so far what happened, we started from photon, then from photon, then we went and we said that, the particles like electrons or protons or neutrons, they have wave nature too. If these material particles have wave nature, now the question is this, that how can we deal them with the classical physics? Because the waves have to be dealt with the wave equation. We can't deal them with Newtonian equations. We cannot, deal them, or we cannot solve them with Newton laws, or Hamilton-Jacobi equations. Now we need to switch to a new way of thinking, and that new way of thinking is we are treated these particles not as a particle, but we will be treating them, and we are treating them as waves. So if we are treating them as waves, then we, Schrodinger was the first who developed a wave equation for the solution of such particles. So for electron, if we have an electron, if we have a proton, if we have a neutron, or if we have an atom. So for all of them, what he said that the particle is not basically described by a classical trajectory, but the particle is described by a wave function. And the solution of this wave function, that is a Schrodinger wave equation. So this gives us what will happen to the wave with time. So it gives us exact solution of the wave with time. So anyway, this was something which was important and which was necessary to be discussed. Now coming a bit further in the same chapter, in the same section, if you look at the last few points, look at here what the book says, that the probability, the total probability, this is probability. As you people remember, I told you people this is probability, and the total probability gives us 1. The total probability gives us 1. So if the total probability gives us 1, dp, we already know that dp is nothing but this thing multiplied by c. And this is necessary and this is mandatory, that this has to be finite. This has to be finite. So, and if you people remember, we talked about this. This is probability density. This is this. And then if this is, if this is finite, then, C, you can easily calculate your C by using this equation. Normalization constant, your normalization constant. For the entire space, the total probability will be equal to 1. The total probability will be equal to one. Now, one thing, here, what the book is talking about, again, the same point that, when we talk about, uh, we are talking about particles. We are not only talking about photons, but we are talking about particles. So particles, classically, they were described by X, Y, Z, V, X, V, Y, V, Z, and they basically, gave us the everything about the particle at each and every instant. Now, what will happen when we talk about a particle? This is not enough. And this will not give us a solution of the problem. Because as we discussed earlier, let's suppose you have a bullet and that those bullets are in a gun and you shoot the bullets on one of the slits. So all the bullets will pass through the same slit and they will hit almost the same place if the gun is not moving. On the other hand, if the gun is for electrons, or the gun is for protons or neutrons or hydrogen atoms or hydrogen molecule or any other, and if we shoot these microscopic particles on the double slit experiment, so we will be not getting the same result. We won't even know that the microscopic particle, electron or proton or neutron or hydrogen atom or hydrogen molecule, passed through slit 1 or it passed through slit 2. We won't know. We will not know at all. So it is totally different world than the classical physics, because now it's no more behaving like a classical particle. So when this is not behaving like a classical particle, it is behaving like a wave, and the wave, because of the wave nature, the things becomes a bit more complex, and the things becomes more, like sophisticated. So we no more know that from which slit these microscopic particles passed. So because the particle is associated with waves, and the wave passes through both the slits. So the wave associated with the particle passes through slit 1, and it also passes through slit 2 at the same time. One thing the book also talks about that, when we talk about photons, so photons can be created and the photon can be destroyed. And this section, this point clarifies that this book is not about relativistic quantum mechanics. We will be not discussing relativistic quantum mechanics. So that's why if we are not discussing relativistic quantum mechanics, then we will be not discussing the creation of particles, and we will be not discussing the annihilation of particles. So this means that the electrons were there, the protons were there, or the material was there. So the material is not created and not destroyed, when we discussing quantum mechanics, especially when we talk about this book. So when we go to the relativistic quantum mechanics, naturally in relativistic quantum mechanics, then we talk about, when the photon comes. So the photon in the vicinity of a heavy nuclei, it basically, it is divided, and the division, basically this energy gives us two material particles. One is electron and the other one is photon. So with these words we are done, and in the next topic we will be discussing about the quantum description of a particle wave packet. But one thing, once again, I want to share with you people that this thing is the most important. This thing is called square integrable. We will be discussing this in the next topic with great details. This is square integrable. So if anything is not square integrable, then that cannot be wave function. So if anything is not square integrable means that this thing is finite. This gives us some value. This gives us some value, whatever the value is, but the value must be finite. This equation, like this, must have some solution, and this must have some finite answer. So this is something, like in the next topic, we will be discussing a lot about this, because usually when we talk about a wave function, so what we do, we consider that, our consideration of a wave function is generally wrong. The book writes wave function, and to tell you truth, those wave function are technically wrong if you consider this concept. So anyway, we will be talking about that in the next lecture. We will be talking about that with more details. So see you and meet you in the next lecture.